So in today's lecture, we will be talking about the alignment. So in the previous lecture, we have already seen that we can have the different kind of the alignment. And we have seen that we are having the major two kind of the alignment. One of the alignment which is known as the global alignment, and the second alignment which is most popularly used, that is the local alignment. Now when we are just going for scoring this alignment, we require some kind of the framework, or we require some system by which we can give the one kind of the measurement to the alignment whichever we are discussing. So for that, historically global alignment algorithm was developed by the Needleman and Walsh. So conceptually this method is similar to the dot plot approach which we have seen in the earlier lecture. In this you can just have the both the sequence on the opposite side, and after that the sequence alignment would be done. So the sequence alignment method predates the dot matrix search, and all of the alignment method in use today are related to the original method of the Needleman and Walsh. So whatever software you are using today for the comparison of the sequence in the baseline, still they are using the global alignment. Similarly, this Needleman and Walsh wanted to quantify the similarity between the two sequences, and over the course of evolution, some of the position undergo base or amino acid substitution, and base or amino acid can be inserted or deleted. So basically, as we are knowing that all the sequences are originated from the one single cell, so during the course of the evolution, there would be some kind of the addition, deletion, or substitution. So depending upon the earlier matrix, whatever we have seen in the last lecture, that is the Palm and Blossom, we are just trying to give score to the entire alignment for the comparison of the sequences. Suppose I want to compare the two sequences. So this is the one string which is known as the string A, and the sequence of that string is the GGAATGG. Similarly, I am having the one another string or the sequence that is having the sequence of the ATG. Now when I want to go for the global alignment, I have to frame out some kind of the rule to give the score to this. So the three simple rule I am creating. One simple rule is that whenever I am getting the match, I will put the 0 marks. Second rule which I am creating, that is whenever I am getting the mismatch, I will put the 20 marks. And the third one is that wherever the insertion and deletion would be there, I'll be adding the 25 marks. So in this you can see that as the numbers are getting increased, you will have the more diversity. And instead of starting from the initial part, we are keeping the psi at the first. So you can see that at both the string I am having the psi. Now I am writing the A T G over here, and other sequence I am writing G G A A T G G on the other side. So this is one kind of the dot plot approach which we have seen in the earlier lecture, that we are just keeping the two sequences on the two axes. Now as per this entire rule, we have seen that wherever the insertion or deletion is there, we have to add the 25. So according to that only, when A is getting inserted in this sequence, I am putting the 25 marks. In the second place, when T is getting inserted, I am adding the 25 to the 25, so it will become 50. So like that only the marks would be added in each one of this. So this is a way by which you can see that on the upper end I am having the 25, 50 and 75, and the lower end I have the range of the 25 to 175. So this is a way by which I can have the first stage of the mark. Now after that, suppose we are going further, then how we are just giving the marks to the other part. So you can see that how we are giving the marks. So what I have to do is I have to compare this G with the position of the A. Right? So in this you can see that whenever I am comparing with the G and with the A and G is not matching. Then mismatch score is 20. So that already we have written that mismatch score is 20. But we are not used to put this direct 20 score over here. What we have to do is we have to add the score of the upper diagonal. So over here I am having the 0. So 0 plus 20, so it will become 20. So like that I have to put the score of 20 over here. Suppose I am going further, then again I can see that the G and A, that is not matching. So the score would be 20. Now 20 I have to add in the 25. So 20 plus 25, it will come to the 45. Same way when I am giving the marks to the each place, I can see that the marks will be coming in such fashion. And after that, we have to just go for the process which is known as the traceback. So the traceback is a complicated process, but for our easy understanding, we are just telling like that suppose I'm getting the 140 score over here, then this 140 score can have the two options. One, it can go to the 140, and one, it can go for the 175, because whatever the higher score is there, that is not the way where we want to go. So that is the simple rule that would be taken every time, right? So whatever the score is there, either the similar score or the score less than that, that should be considered. So you can see that from the 140 I can have the two options, 140 and 75. Now again suppose I'm going from 375, then again have the two more score. So upper part I can get the score 75 and other places are more than 75, so I'm not going to this place of the 190 or 120. Again from the 75, suppose I'm going upper, then I can have the score of the 75 and the lesser than 70 is available, so this is a place where I can go. So like that only we have to just go further, and when you are just going for this entire part, and when you are just aligning both the sequences, then you can see that wherever the same scores are coming at this place, I am having the same kind of the sequence. Suppose 140 is at the two places, so it is reflecting that there are 2G. Same way, suppose I am getting the 75 at two places, so it reflecting it is having the A. So like that only, wherever the same place would be there, the chances are like that you can have the sequence. Now as we have seen that we have taken the very small sequence, suppose I am getting this upper sequence and lower sequence, then I can have the major 4 probability. One, the ATG is matching at only one place in this, that is the ATNG. Other places I can keep the gap. So that is one element which I can have. Why it is known as the global? Because we want to compare the all the ATG together, right? The second portion is that I can see that there would be one ATG, but after that there would be again G. So there is a probability that I can insert one gap over here and still G can match over here. So that is the second probability. Same way, suppose I'm going to the third probability, then you can see that even before this I'm having the 2A. So for this A also I can explore that possibility that 1A I can take, after that I can add the gap and then I can add the TNG. And last property is that I can insert the gap at both the places, that I can match this A, I can match this T and I can match this G. So these are the four properties which will come, and mathematically it can be cleared out from this kind of this code. But as a biologist, we are not going in the process of this mathematical programming either. But by this programming only, the two sequence would be getting aligned with each other. So that is a basic thing about the global alignment. Now, why global alignment is useful and why it is having some problem? So the usefulness of the global alignment is that we are comparing the entire sequence. At the same time, problem you can have that you can have the more than one option in this, and again that is a very time consuming process when we are just talking about the computational power and the time to perform it. Now we are just going for the second alignment. The second alignment is the local alignment. So as we have seen in the earlier lecture, that local alignment is basically looking for the similarity in the substring. So instead of comparing the entire sequence to the entire other sequence, whatever the local sequences are getting matched, that we are trying to match. And for that, the Smith-Waterman algorithm is utilized. So Smith-Waterman dynamic program is used for the local alignment, and this algorithm gives the highest scoring at the local match between the two sequences. And Smith-Waterman can be used instead of the Needleman and Ross for matching the two sequences that have match region that only a fraction of their length and that overlaps, or where one sequence is a fragment of the another. So that is the basic speciality of this Smith-Waterman algorithm. So it can be utilized for the comparing the local sequences. Now what can we do in this? So in this also we are having the same kind of the dot plot approach. So I can put the ATG sequence and I can just have the other part, right? Now with this, as we have seen earlier, that in the case of the global we want to compare the entire sequence, and in the case of the local alignment we are just comparing wherever it is getting match. So what we are trying to do is, for the match I am giving the some score, and for the mismatch I am just giving the minus score, right? And I am not giving any score for the insertion or deletion, because we are just comparing it wherever it is getting matched. So when I'm just using this rule, you can see that instead of the earlier one where I'm adding the 25 25 to each one, here I'm putting the 0 at the both the place. The initial first line would be 0. Then second rule what I'm doing is that whatever the mismatch is there which is having the score in the negative value, that I'm putting in the 0. Suppose I'm going for the scoring like this, then you can see that picture like this, that suppose I'm getting the G over here and A over here. So G and A both, they are not getting matched, and when they are not getting matched, as per this mismatch I have to give the minus zero point 0.5 score, and minus zero point 0.5 over here it will come plus 0. So minus zero point 0.5 plus 0 means it is minus zero point 0.5, and that I am just summing up to the 0. So like that, when I am giving the score to the each and every place to this, I can have this maximum score over here. And as we have seen in the earlier, that whatever the maximum value 3 is there, that I can take as a starting point. From 3 I can just go to the lower, so the nearest position is the 2, and again from the 2 the nearest position is the 1. So like that, suppose I'm going for the comparing, then I can see that this ATG is matching at only one places. So this is a small sequence. So visibly also you can see that local alignment, it will give you the one perfect place where your entire sequence can get matched with the maximum kind of the scoring mechanism. So this is a way by which local alignment comparison is done. So even though it looks very simple, but when we are just performing it in the computer and the sequence length is of millions of sequences, then in that case that becomes quite difficult to manage. So that is the reason that we require the even computational power very high, and even in some cases we require the supercomputer for analyzing this kind of the sequences. Now we have seen that by this logic, at least we came to this third level of the comparison. So initially we have started with the simple alignment. Simple alignment means wherever it is getting match, I can put the line. Wherever it is not getting match, I can put the zero. So that was the first slide which we have discussed in the last lecture. After that, slowly we came to the concept that wherever it is not getting match, we can put some kind of the blank and we can just go for the process which is known as the alignment. Then we have seen the alignment of the pair alignment of the two sequences. Can we have the global and local mode? And then again we have seen that wherever we are going for the protein, each and every replacement cannot given only the 0 and 1 in case of the amino acid. For the each amino acid we are just supposed to give the different score according to their biochemical property, and in that we have seen the example of the palm and blossom. So that was the substitution matrices, and after that by using that kind of the matrices it is possible to run the Needleman and global algorithm. So whatever the scoring matrices we have used, that is just for your understanding, we have taken a very simple one. But when you are using it in a practical, you are supposed to use the palm and blossom matrices. So by that we were able to compare the two sequences. But still our problem is not getting solved. Because whenever we are just having the real life science example, that suppose today I'm finding out some new gene, and after that I want to find out the function of that gene or the origin of that gene, then I have to compare my one sequence with the millions of the sequence in the database. So for that we require some other kind of the software, and in that series only most two popular softwares are utilized, that is the FASTA and the BLAST. The purpose of this both the software is to compare your one query with the millions of the query which is available in the database, and to find out that which is the best scoring sequence with you. So the first of all we'll be discussing the FASTA. So FASTA is the powerful tool for the scanning the database to find out the sequences that are similar to the query sequences. It is generally best to make the protein-protein comparison, but FASTA can also compare the DNA sequence also. And the related program tFASTA allows the protein query sequence to be compared with the DNA database. So in the tFASTA, what will happen? That whatever the protein query is there, that is computationally transferred into the DNA sequence, and after that we can compare it with the DNA database. So that is a way by which even you can compare the protein to not only protein sequence, but you can also compare the protein to its gene or the DNA sequence. Each DNA sequence in the data bank is translated in all the 6 frame, and then 6 frame protein compare the made with the FASTA, and this is generally the best way to scan the EST database. EST stands for the express sequence state, right? So for the finding of the EST comparison, the FASTA can be utilized. So we'll be just taking the entire detail of the FASTA, that how it is work. So basically it will have these four kind of the steps. In the first steps, as we have seen in the earlier, it will be just comparing one to one sequence, but that would be compared with the dot plot approach. So I can just put one sequence A over here, and I can just put the second sequence B over here, and after that I can go for the comparison. Suppose I'm not using any other kind of the logic and I'm just comparing one to one sequence entirely with entire millions of the sequence, then it will take very long time to complete the task. So for that reason, the FASTA uses the method which is known as the word-based method. So it looks for the matching of the sequence pattern of the word, which is also called as the K-tuple, and then attempts to build a local alignment based upon this word match, right? So what can be done inside this? That suppose I want to compare the two sequence. We can just take the simple example that suppose you want to compare my name Rajesh Kanjibai Patel with the entire database where the name of the so many peoples are there already stored. Now suppose you are just going for the simple comparison, then you have to just align Rajesh Kanjibai Patel with each and every person name which is having the Rajesh Kanjibai Patel or whatever it may be. Suppose you are taking the telephone directory, then you can have the millions of the people. Now Suppose you want to reduce it, then what you can do is instead of comparing the entire sequence Rajesh Kanjibai Patel, you can take the few words from the each one of this. That for example, from the Rajesh you are taking the AJ, Kanjibai you can take the KAN, and from the Patel you are taking the PAT. Now instead of the comparing the entire sequence, in the first step what we can do is you can just find out the comparison of this word only. So this word Raj, Khan and Pet, that can be known as the K tuple. So what I'm doing is I'm just comparing only this three word with the entire millions of the sequence. So suppose in sequence I'm getting the 1 lakh sequence, but out of the 1 lakh sequence, only for example 10,000 sequence are having all these three words. So what I can do is from the 1 lakh sequence, I can just remove all the 90,000 sequence and I can select the 10,000 sequence for the further comparison. So that will be reducing my job in both the way. One, instead of comparing the full length sequence, I've compared only the word. Now whatever the word I have compared, from that I've just reduced the entire database from the 1 lakh to the 10,000. So that is the first step which is normally done.